Hello Paul, this is Xavier. Hello everybody else from the community of developers following this excellent series of lessons about programming Raspberry Pi with Python, and the subject was to play a little bit with bits, yes, and associate this with lighting, turning on and off LEDs. To have also experimentation on GPIO pins on the Raspberry Pi. So where do we start from here? Yes, okay, I take this and the sketch here. Yes, more room for us. What could be interesting to illustrate this, first of all, take this. Oh, it's all black. Yes, I take this. It's my prompt command, so I start Python here. Okay. Just to show you that you can use the bin function here to get the binary representation of a decimal value. For binary 4 is 100. Remember here 100. This one means 1, this one means 2, this one means 4. Okay. So the rank here gives a value to the bit. Which we can see with any value here. Okay, why do I... Whoa, I don't have the right index here. I say bin 8. It's 1 followed by 3 zeros. Bin 9 will be 1 followed by 2 zeros and 1. Okay, which is 8, no 4, no 2, and 1, which is 9. Okay, why do I talk again about all this? We have a shift operator, a binary shift operator, which is shift to the right or shift to the left. Okay, if you have this value 100 and you shift to the right, it will become here 10. If you shift to the right by a value of 1, and if you shift again to the right by the value of 1, it would become 1. It's just a shifting of the bytes. Okay, which means that if this means 4, decimal, and we shift the value by 1 rank to the right, it will become 10, which is 2. Okay, let's check. Let's check. I take back this. Okay, I take 4 and I shift by 1 position to the right. It gives me 2. Okay, appears consistent. And of course I can shift back to the left. It's the same principle. If I take 2 and I shift to the left by 1 position, it becomes 4, etc. If I take 9 and I shift to the right 1 position, it becomes 4. Okay, because 9 here, 9, where was it? 9 was 1, 0, 0, 1. Okay, we shift 1 position to the right. It means that this disappears. So it becomes 1, 0, 0, which is 4. Does it make sense? I hope it does. It's fun playing with bits and balls too. So what can we do with this? It's very interesting because our 4 LEDs will be represented by will represent half a byte, which is a series of 4 bits here. So we can consider that if we use a word of 4 bits here, which is half a byte, or a nibble, we can play with those binary operators to analyze the value of each bit in this word, in this nibble. Okay, and if we remember that when turning on or off a GPIO pin is just giving it a value of 0 or 1, in fact true or false, but it's more or less the same in this context, especially in a weakly typed language like a Python. We have all the tools needed for our goal. So let's have a look at the code here. Just changing the screen. Okay. What did we do here? Okay. I just initialize here my pins in an array, so I can work either with a GPIO or with the pins. It's the same. I use 17, 27, 22, 21. I defined a function here which is able to get a nibble in first parameter and a rank. The rank, I mean by the rank the order of the bit. The first one on the right in this configuration will be order 0, order 1, order 2, etc. So the idea is to analyze here the nth bit of the nibble and return here a tuple with the rank and either 0 or 1 following the state of the bit. Okay, so if the rank here is greater than the size of the nibble, we will have a value error here and return the rank with a value 0, just to leave it off. Okay, but normally we should not get that far. Okay, and that's where we analyze here the value of the bit of interest here. Okay, and we combine this with 1. Okay, why is that so? Why is that so? Just because this value here can be 0 or 1, and if we combine it with 1, the result will be true or false, 0 or 1. Okay, then how we do use this? Just here for we just initialize all our pins, looping on the pins array. I defined also here a function to reset the LEDs, just to make them all off here. And then I loop here from 0 to 15, which is a range 0, 16, of course, but I will have 16 values here, which is the maximum that can be represented with a half a byte. For each value, we will loop on each bit of the value, calling here the function bitison that we explained earlier here. Okay, and I loop on each value, and for each value I loop here for each bit in the, I would say, byte in the nibble. Okay, yeah. That's it. So this is a comprehension list, which is easier to express, and we will loop on the result of this comprehension list. Replace this double loop at this stage. Okay, and this time I can here turn on off the pin, corresponding pin, with I here ranging from 0 to 4, or 1 to 4, sorry. Okay, then I will just leave a little delay just to be able to read visually the LEDs, and then I reset. Otherwise it will always be eventually be all lit up, which we don't want. We want a specific value at each iteration of the main loop here. Okay, so let's have a look. Here you can see that I choose to use 4 separate resistors. It's a better design, because if you use just one resistor, it's in serial, it would work also, but you can have little differences even for the same LEDs from the same manufacturers. You can have little differences in a resistance. So if one of the LEDs has a lesser resistance, it will draw more current, so it will burn stronger. It will have yes, and it will reduce its lifespan. Also, problem is that if you work in series here and one of the LEDs burns, the others cannot go on working. They don't have current anymore. Here, if one of the LEDs burns out, the other can go on working, keep on working. Okay, it doesn't open the circuit. Also, problem too is that if you work in series with one resistor, this unique resistor will draw the sum of all the currents in LED. So if you have 20 milliamps by LED here, it would make 80 milliamps that would be drawn through the unique resistor, and then you need a stronger resistor. But these details are, of course, here we don't have these programs, but it's can be interesting to think a little bit about this. Okay, let's check the working here. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and that's it. Oh, sorry, the camera is reversed, so we had it in the wrong way, maybe. If I turn on the camera, it will be more consistent with our initial project. Now let's do it once again. One, 2, 3, 2 plus 1, 4, third bit, 5, 6, 4 plus 2, 7, 8, the fourth bit, 9, 8 plus 1, 10, 11, etc. Okay, fantastic, isn't it? And that's the beginning of a big story. Okay, thank you for watching, and I'll see you soon, maybe this afternoon, for the traditional meeting. Bye. Always with coffee.